Now let's do one example for air standard diesel cycle. Again, you see the word air standard, which means the gas inside the cylinder is air, and you can use air properties for your calculation. We know gamma, which is the compression ratio, is 18. You can see this number is much, much bigger than the compression ratio when we had a gas engine. For a gas engine, the value was about 8. For a diesel engine, this value is 18. That's why diesel engine usually has a much higher efficiency than the gas engine. Gamma C, which is cutoff ratio, is equal to 2. At the beginning of the compression stroke, temperature is 300 K and pressure is zero point 0.1 megapascal. K, the ratio of the two specific heats, is 1.4. First, sketch the process on P versus nu and a T versus S diagram. Part 2, look for temperature and pressure at each point. And part 3, look for efficiency. Part 1 is actually the easiest one because when you sketch the two diagrams, nothing changes from what we did earlier. Since there's no phase change, nothing changes. So what you can do is just copy and paste. You can just copy that from our notes. 421, 122, 223, and 324. 122 is isentropic, 324 is isentropic. And then again, on T versus S diagram, everything's still the same. 421, constant pressure. 122, isentropic. 223, constant volume. And 324, isentropic. So this is the diagram. It's exactly the same as what we did earlier, and nothing changes since there's no phase change. And then part 2. Part 2 is to look for temperature and the pressure of every single point. And actually, we are given the temperature and the pressure of one point. But the question is, which point is this? The problem says the beginning of the compression stroke. Compression stroke is process 324. So the beginning must be number 3. So what is given is T3 and P3. They are given. So we're done with one point already. So now we have point 3. Which point do you want to move on to? Probably number 4. Why? Because 3 to 4 is isentropic. And for isentropic, we have additional equations. So next, we move on to point number 4. Okay, the equation we have is T4 over T3 equal to gamma k minus 1. So from here, we can actually find T4. Plugging T3, 300 Kelvin. Gamma is 18. Index is 1.4 minus 1. So solution to T4 is 953 Kelvin. So now we've found the temperature of T4. We need to find the pressure of number 4. We have temperature. We're looking for pressure. What equation goes to your mind? Ideal gas equation. Can we use that? Yes, because air is ideal gas. So let's apply ideal gas equation. PV equal to mRT. We're going to apply this equation twice. The first time to number 3 and second time to number 4. What we do next is left hand side divided by left hand side must be equal to right hand side over right hand side. And now we can tell you can cancel MR, MR, and from algebra, we can move P4, the one I'm looking for, to the left-hand side, and everything else to the other side. That is P3 times V3 over V4 times T4 over T3. We do have P3, we do have T4, we do have T3. We just don't have V3 over V4. But what is V3 over V4? Let's go back. V3 over V4 is the definition of gamma. So we do have gamma, P3 times gamma, T4 over T3. So now let's plug in the numbers. P3 is 0.1 megapascal, so times 10 to the 6 to convert it to Pascal. Gamma is given, that is 18. T4 is 953 Kelvin. Make sure you use Kelvin for temperature. T3 is 300 Kelvin. So our final solution for P4 is 5.718 times 10 to the 6 SI unit, which is Pascal. So it is 5.718 megapascal. That is P4. So now we're done with point number 4. We're done with number 3, number 4. Next one, which point should we move to? Probably number 1. Why? Because 4 to 1 is a constant pressure process, so P1 must be equal to P4. P1 must be equal to P4. That is really easy. 5.718 megapascal. So now we have pressure P1, we're looking for temperature T1. We have pressure, we're looking for temperature. What equation? Ideal gas equation. PV equal to mRT. And again, we apply this equation twice. First time we apply to number 4. Second time we apply to number 1. And then we do the same thing. Left hand side divided by left hand side equal to right hand side over right hand side. So you can see we will cancel MR. We will also cancel P4 and P1 because P4 is equal to P1. So now we can easily find T1. T1 is actually equal to T4 times V1 over V4. We do have T4, but what about V1 over V4? What is V1 over V4? Let's go back to before. V1 over V4 is actually the definition of cutoff ratio gamma C, and it is given T4 times gamma C. T4 is 953 Kelvin and gamma C is 2, so the solution for T1 is 19 and 6 Kelvin. Okay, so now we're done with point 1. The only point that is left is point 2 now. We will probably build a connection between 1 and 2. Why is that? Because 1 to 2 is an isentropic process, and we do have additional equations for isentropic processes. The equation is T2 over T1 equal to gamma C over gamma with the index of k minus 1. So from here, we can easily find T1, T2. T2 is equal to T1 times gamma C over gamma with the index of k minus 1. Plug in the numbers. Solution to T2 is 791 Kelvin. So now we have temperature. We're looking for pressure, P2. What goes to your mind? Ideal gas equation. Very good. First of all, you have to apply this equation to number 2 because we're looking for T2, so we have to have T2 show up. And then we apply this equation again. Okay, to which point do you think that is actually easier for us? Let's take a look. 2, 2, 3 is a vertical line on P versus nu diagram. So V2 must be equal to V3. If we apply this equation to number 3, our calculation will be easy. Why? You can take a look. So now let's do left hand side over left hand side equal to right hand side over right hand side. We can cancel MR just like before. We can also cancel V2 and V3. Why? Because V2 is equal to V3. 223 is a heat loss process at constant volume, so V2 must be equal to V3. And from here, we can easily find P2. P2 is equal to P3 times T2 over T3. And what is P3? P3 from before is given is 0.1 megapascal. So convert it to Pascal by multiplying 10 to the 6. T2 is 791 Kelvin divided by T3, 300 Kelvin. So our solution for P2 is 0.263 times 10 to the 6 SI unit Pascal. One more step, 0.263 megapascal. So now we've found the temperature and the pressure of every single point. We can summarize everything. T1, P1, T2, P2, T3, and P3, and T4, P4. Okay, so that's part 2. And part 3 is actually very easy. Part 3 is to look for efficiency, and we do have an equation for that. Copy down this equation. And then plug in numbers. And the solution to efficiency is 0.632. So now you can see the efficiency for this diesel engine is 63.2%, which is much higher than the previous example when we had a gas engine. The efficiency was about 50%. The reason why diesel engine usually has a higher efficiency than the gas engine is it has a higher gamma compression ratio. The higher the compression ratio is, the higher the efficiency will be.